Good afternoon, everyone. Welcome to the College of Engineering Virtual Brown Bag Series. I'm the host for today. My name is Gautam Das. I'm the Associate Dean for Research, College of Engineering. And it's my great pleasure to invite our speaker for today, Professor Michelle Hummel. She is an assistant professor in our civil engineering department, and she's going to talk about a topic which is, and I don't know a whole lot about it, but I plan to learn as much as I can. Sounds exciting. It's adapting to coastal change, opportunities and challenges for coupled human-natural systems. So before I talk about the abstract and also a little bit of the bio of our speaker, just wanted to let you folks know that the talk is going to be for about maybe 40-50 minutes. And we will have some time for questions. So please hold off on your questions and type them into the chat window. And at the end of the presentation, I'll have the opportunity to read them out to our speaker and she will get to answer them. And this entire presentation is going to be for an hour. So I'm hoping that we'll have some lively discussions at the end. So Dr. Hummel is an assistant professor in civil engineering at the University of Texas at Arlington. She holds a bachelor's in civil engineering from Case Western Reserve University and a MS and PhD in environmental engineering from UC Berkeley. She is broadly interested in understanding how coupled human-natural systems respond to climate-driven disturbances in coastal regions. Interesting stuff, I have to admit. Current research project focus on coastal and estuarine hydrodynamics, compound flood modeling, sea rise level adaptation, critical infrastructure disruptions, and community resilience. She has received funding from the National Oceanic and Atmospheric Administration, Texas Department of Transportation, and the U.S. Coastal Research. As I mentioned, her title, I've mentioned that earlier. I will spare describing the entire abstract. I will leave it to Dr. Hummel to maybe describe the topic through a presentation. So, Michelle, it's all yours.
All right, thank you very much, Dr. Das. Hopefully my screen is showing up okay here.
It is.
All right, perfect. Yeah, so as mentioned, I'm Michelle Hummel from the Department of Civil Engineering. And today I want to discuss some of my research related to how coastal communities respond to climate-driven changes and what are the opportunities and challenges that we have as a society to hopefully build resilience and adaptability to these changes that we're seeing along our shorelines. So when we look globally at the population living along coastal regions, we see that it has been increasing over time. And in the US alone, approximately 40% of our total population lives within coastal counties, even though those coastal counties only comprise about 10% of the US landmass. So there is a high concentration of population in these coastal regions. These areas, as you can see by the numbers shown here, are also centers of economic activity, and they contribute substantially to employment and also to the production of goods and the transport of goods as well. If we look at other parts of the global coastline, we see even denser development, particularly in parts of China and Southeast Asia. So really this is a global issue where we're seeing higher concentrations of populations along our coastline, as we're also seeing some additional hazards created along these coastlines, which I'll discuss here in a second. So within many of these coastal communities, much of the natural coastline has been altered to make room for homes and businesses, and also the critical infrastructure systems that are necessary to support them. So this is an image of Miami. You can see that it's highly developed along the shoreline here. And in addition to that, the critical infrastructure that I mentioned includes extensive networks of roadways, as well as water and wastewater systems, electrical substations, and ports, many of which are located right along the waters here. So due to the historical placement of our communities and our buildings along the shoreline, these structures are often susceptible to coastal flooding and associated damages. And that's particularly true when we think about storm surge due to hurricane events, which have led to widespread devastation along the east and Gulf coasts of the US. So over the past 150 years, as we can see in the graph here, the number of tropical storms, and in particular, the number of very severe hurricanes of Category 3 or greater has increased over time. So you can see the increasing trend here. And that has been occurring at the same time that development along our coast has expanded. And so when we see that intersection of increasing hazard plus additional development and people located within those hazard zones, that means we're seeing more costly disasters. And even in areas where we don't have hurricanes or tropical storms, like the US West Coast, rising sea levels have led to more frequent high tide or sunny day flood events. And even though these events are not immediate or as immediately destructive as hurricanes, they're still a large burden to residents, and over time they can cause serious deterioration of infrastructure. So cities like San Francisco, Miami, which again is shown here, and Hampton Roads in Virginia are already dealing with these issues related to high tides, and they will only become more severe as sea level rise progresses into the future. So to summarize this challenge for our coastal regions, we have very dense human developments that contain very important infrastructure systems and also support critical economic sectors like tourism, energy, and shipping. And these areas are very susceptible to intensifying flooding threats due to both short-term shocks like hurricane events, as well as longer-term stressors like sea level rise. So with this in mind, coastal communities are now tasked with figuring out how they should best adapt their shorelines to be more resilient to these future flood events, and then to also mitigate the impacts to people and property. So when coastal managers are thinking about how to adapt their shorelines, they have a variety of different options. One of those options that has not really gained widespread support yet, but may actually provide the most substantial long-term benefit, is strategic retreat, which means that communities actually relocate away from the coastline further inland, and then hence remove themselves from the coastal flood hazard. However, at this point in time, most communities are not considering retreat. They're mostly focused on protecting their existing infrastructure through shoreline modification. And so that's what I'm going to focus on within this presentation. So when we think about how we can protect our shorelines, these approaches can take many different forms, and they're categorized. One way of categorizing them is using this typology shown here. So here on this horizontal axis, we have a range from static to dynamic. And so static structures are structures that remain in place and they don't require active monitoring. On the other hand, when we look at dynamic structures, those are structures that can move over time and may also require active operation. If we look at the vertical axis here, that spans from landforms to walls. So landforms include earthen structures or natural features, and then walls are more highly engineered. So just to look at each of these, if we take this quadrant in the upper left corner, static walls, those include seawalls or flood walls, which are usually constructed out of man-made materials like concrete. So this is an example of the Embarcadero seawall in San Francisco, which protects much of the city's shoreline. We also have, on the static side, static landforms, and these include levees and dikes. They often have sloping profiles on the coastal side, as you can see here, sloping down to the water. And then they can be topped by infrastructure like roads or buildings. So this is an example of a super dike in Japan. Then if we look at the right side of the matrix, we have dynamic walls like tide gates or movable surge barriers. that are operated to prevent coastal flooding. So one example is the Thames Barrier Tide Gate located near London, as you can see here. And there was also another recent storm surge barrier that was completed in Venice, Italy, and was deployed a few months ago to prevent flooding in that city, which is also dealing with a lot of tidal flooding issues. And then finally, we have dynamic landforms, and these rely on natural systems like beaches or sand dunes or marshes to provide protection. And these systems, because they are natural, they're constantly changing in response to different inputs like waves and surge, different amounts of sediment, and also different river discharges. So one example here is the sand motor in the Netherlands, and this is a coastal protective structure that uses sand to provide protection for the shoreline here. And you can see through this image how dynamic it is. It's really changing over the past 5 years. It's changed and built up quite a bit as a result of changes in the sediment inputs and changes in the wave conditions. So as engineers and coastal managers, we have a good grasp of how to design and manage structures in these 3 highlighted quadrants because we've been doing that for many decades. However, our understanding of how to design and maintain structures within this dynamic landform category is still rather limited because their response to changes in water level or changes in sediment is more variable, and it can differ quite a bit from one location to the next. So even though there is an increasing emphasis on thinking about how we can use natural features to protect our shorelines, there's still a lot of work to be done to understand how we can most effectively integrate these types of structures to mitigate coastal hazards. So when we consider which of these shoreline adaptation strategies to implement, whether that be a static versus a dynamic system or a landform versus a wall, it's important to remember that these coastal regions are what we call coupled human-natural systems. And this means that whatever decisions we make about how to manage our shoreline, those could lead to feedbacks within the natural system that then affect future patterns of flooding and flood-related damages. However, in most cases, these feedbacks are currently not really well understood or quantified, and as a result, they've not been incorporated into project planning or implementation, at least to date. And this has the potential to impose unintended impacts, which are also sometimes called externalities, on other parts of the shoreline, as an action or an implementation taken at one location could potentially increase the risk of flooding for someone else in another location along the shoreline. So just to kind of give you an example of this, this is a historical example that has been seen across many river systems in the US. So in order to provide flood protection, there has been a lot of historical levee building along our river systems. And the figure here on the left is showing the flooding that would occur for a particular storm in the Wabash River, located in Illinois and Indiana. And this is the flooding that would occur before any levee building happened. So this is sort of the natural system where the floodwaters are able to move into the floodplain. And then if we look here on the right, you can see in orange, these are the levees that were constructed to protect industry and other developments and cities located within this region. And so they have provided protection for these particular areas that are located behind the levees. But we also see highlighted here in red that they've actually led to additional flooding in other parts of the watershed, as water that would typically flood these now protected areas is forced to move elsewhere. So while we see a reduction in flooding for people behind the levee, we can also see increases in flooding for other communities that are not as lucky to be protected by those particular structures. So this sort of consideration has been noted along river systems, and it's also present in coastal systems, particularly estuaries and bays, but it hasn't really been studied as extensively in our coastal systems. So there's a real need to understand how do the shoreline actions that we're taking affect flooding and the potential for damages along other parts of these developed coastlines. So how do our decisions at one location affect what happens at other locations? So with those challenges in mind, I want to focus our attention for the rest of the talk to the San Francisco Bay Area in California, which is a really great illustrative example of these processes and interactions that I've just been talking about. So you can see here, this is the San Francisco Bay Area in California. It's the largest coastal estuary in California, and it's highly developed. So there's about 7.5 million people living along the shoreline or in the counties surrounding San Francisco Bay. The bay itself is comprised of 4 different sub-embayments. So we have the South Bay, the Central Bay, San Pablo Bay, and Sassoon Bay. And as you can see on the right here, we have 2 different inputs of water. We have water coming in from the land from further inland through the rivers, the Sacramento and San Joaquin rivers and the Delta. So this water passes through that Delta, moves into Sassoon Bay, San Pablo Bay, and Central Bay, and then exits through the Golden Gate Inlet into the Pacific Ocean. And then from the other direction, we have tides that enter the bay through the Golden Gate Inlet, and then they split and either travel north as a progressive wave through San Pablo Bay or south as a standing wave through the South Bay. And this standing wave is actually amplified as it moves from the coast down to the south part of the bay. So water levels are higher down here at the south end of the bay than they are at the entrance to the bay. So we see within the system that there are very distinct tidal regimes depending on whether you're in the north part of the bay or the south part of the bay. And in addition, we also see fairly large variations in the amount and density of development. So you can kind of see in this satellite image that there's a lot of infrastructure and development surrounding the South Bay. But as we look into the northern part of the bay, there's more agriculture and marshlands, so it's not quite as developed as the South Bay. So just to give you some perspective on how much development is located here, this is an aerial image of downtown Oakland in Central Bay, so very developed all the way down to the shoreline. We also see that there are critical infrastructure assets located right along the shoreline. Those include bridge approaches that connect communities on the eastern and western shorelines, as well as infrastructure like wastewater treatment plants that are constructed on reclaimed marshlands. And the region is already experiencing tidal flood disruptions that have led to major delays and road closures. Certain parts of the shoreline are susceptible to permanent inundation with even just a small bit of sea level rise, less than 50 centimeters or so. And so recognizing all of these threats that I'm just talking about, local decision makers are currently trying to decide how can they best adapt to future flooding, and is that adaptation best managed by individual communities, by the region as a whole, or at some intermediate scale between that. And so we wanted to try to help inform that decision and the thinking about how to proceed with sea level rise adaptation. And so to start to address this and determine what type of feedbacks exist between shoreline management and flood hazards, we've applied a coupled modeling approach that allows us to simulate how the bay will respond to different shoreline modification scenarios, and then to also map the resulting impacts on the built environment. So to do this, we start with a hydrodynamic model shown on the left, and this simulates how the tides propagate through San Francisco Bay. So as the water comes in from the ocean, how does it move through the bay? Which parts of the landscape are inundated or flooded, and which ones remain dry? We then use this model to simulate a range of sea level rise projections for the region. And we also modify the shoreline in the model to represent a range of shoreline protection scenarios. And to do this, we assume that one segment of the shoreline is protected by a seawall, while all of the other areas remain with their existing shorelines. So you can see in this map here, we have a bunch of different shoreline segments highlighted, and for each one, we just protect its shoreline by a seawall and then allow the rest of the bay to maintain its existing infrastructure. And then we can understand how does that one action affect the patterns of flooding and damages that we see elsewhere. And so we compare the model results from that particular protection scenario with the present day scenario to see what the differences and impacts would be. And then finally, we combine those flood outputs with models of infrastructure and also building stock data to assess how the built environment would then be impacted by each of those scenarios. So before I jump into the results, I just want to give you a sense of what these different shoreline segments look like and how they vary across the bay. So we've implemented, as I mentioned, 30 different shoreline segments across the bay. And each of these segments is considered an operational landscape unit, or an OLU. So I'll be using the term OLU throughout the rest of the presentation. And the idea behind these operational landscape units, or OLUs, is that they represent cohesive units of physical and ecological characteristics that provide a certain set of ecosystem services. So, for example, if you think about a shoreline segment that is fronted by a marsh, that marsh might be fed by a particular river system. It might have a particular sediment source and provide habitat for a certain subset of native species. And so we want to think of that system in its entirety as a whole unit that can provide those benefits, rather than arbitrarily dividing it up just based on city limits or jurisdictional limits. And so that allows us to maintain the integrity of that ecosystem and ensure that it's maintained as a single unit, and also allows that ecosystem to hopefully provide benefits back to the neighboring urban system as well. So in the case of San Francisco Bay, as I mentioned, we have these 30 different OLUs. And these OLUs can be classified into 3 different categories based on their prominent landscape features. So you can see those here. The first geomorphic category is called a headland and small valley. Those are shown here in green. And if you look at this first panel on the right, these typically have very narrow baylands and steep slopes, which means that there's relatively limited room for flooding. So this is an aerial image of one of those. You can see that the topography rises pretty steeply right from the shoreline. And so there's not really much low-lying area that could be flooded within these OLUs. Secondly, we have alluvial fans and alluvial plains. These are represented by red here, and these have moderately sloping baylands and are typically backed by steeper hills. So this is an example from the eastern part of San Francisco Bay, where we have moderate width for development, some low-lying areas along the shoreline, and then we have the hills in the back. And then finally, we have wide alluvial valleys, which are shown in blue. These have wide, gradually sloping baylands, and they could include tidal marshlands and mudflats, as you can see in this image here. So there's a lot of low-lying area, a lot of room potentially for floodwater storage within these units. So by individually protecting the shoreline of each of these OLUs in our hydrodynamic model, we can then determine how the tides and flooding are affected, which will help to inform future adaptation projects. All right, so let's take a look at some of those results. Here I'm showing the results of that analysis for a 150 centimeter sea level rise scenario. So this is on the higher side of the projections for sea level rise. Again, we're individually protecting each of these shorelines, and then here we're mapping the change in water level that occurs across the entire bay as compared to the existing shoreline scenario. So the numbers here, or let me just say that in this legend here, if you see areas that are in red, that means that water levels have increased in the bay as a result of protecting that shoreline, and blue colors indicate that water levels have decreased as a result. And then the number in the corner here shows the OLU number that is protected, and the letter indicates the landscape type. So H for headlands, A for alluvial valleys, and W for wide alluvial valleys. So when we look at this collection of maps, there's a couple scenarios that immediately jump out due to the large increases in water level that we see, so indicated by the red colors that you see here. For example, OLUs 7, 9, and 10, which are located here along the northern part of the bay in North San Francisco Bay. Those lead to, or protecting those shorelines leads to relatively large increases in water levels within the North Bay. And then similarly, when we protect OLU 22, which is located down here at the south part of the bay, we also see local increases in water levels in the South Bay. So all of these 4 scenarios or OLUs are considered wide alluvial valleys. So they all have this sort of low-lying, extensive bayland system. And as a result, they have a lot of floodwater storage space due to those shallow landscapes. So when we block off the shorelines in these areas and prevent water from flooding these low-lying regions, that means that we're causing or forcing that water to go elsewhere, and that leads to higher water levels in other parts of the bay. So given the large impact that we see in terms of water levels when we protect wide alluvial valleys, we also can look more closely at these scenarios to understand what their regional impacts are in terms of flooding and damages throughout the bay. So for these maps, I'm showing 2 of those scenarios from the previous slide. So protecting OLU 7 shown here in the hatched lines, and then protecting OLU 22 in the South Bay also shown in the hatched lines here. And so when we look at these maps, we can then see how the flooding depth around San Francisco Bay changes when these particular shoreline segments are protected. So again, on the left here, we see protection in OLU 7. These red areas indicate the most substantial increases in flood depth, which typically occur in the North Bay. But we also see yellows and oranges that also indicate increases in flood depth, and that typically occurs throughout much of the rest of the bay, particularly here in the South Bay. So just by protecting this one shoreline in the north part of the bay, we're causing additional flooding for all of these highlighted areas here throughout the rest of the bay. On the right, then, we see that the South Bay shoreline segment protected in OLU 22. This also leads to additional flooding in other areas, and the strongest impacts now are seen in the South Bay. So as these examples demonstrate, local shoreline protection actions and armoring actions can shift flood hazards to other shoreline segments, and that can occur both locally near the protective action as well as regionally throughout the rest of the bay. But what does this shift in flood hazard really mean for communities? So here we're now looking at the change in economic damages that occurs as a result of those same 2 protection scenarios from the previous slide. So we see that changes in damages are more variable across the region because they depend not only on the patterns of flooding that we previously looked at, but also on the amount of development that is concentrated along each part of the shoreline. So we often see that areas that have a lot of development, a lot of valuable land located right along the shoreline, those areas have higher damages as a result of these flood interactions. And in the most extreme case, if we protect this shoreline here in OLU 22, that leads to over $700 million in additional damages when aggregated across the entire bay, which represents a very substantial cost for the region. So just protecting this one part of the shoreline can have potentially large repercussions for communities throughout the rest of the bay and lead to unintended consequences. In addition to economic damages, population impacts are also a major concern for coastal communities. And there's really a recognized need that we need to understand how vulnerable populations will be affected by sea level rise and coastal flooding. So here, let's consider again the North Bay OLU 7 scenario. And in the graph on the right, here, we're looking at the number of people who benefit or are impacted by this protective action. So the left columns represent the people living in the protected zone, so living within this hatched region, who would benefit from shoreline protection at these 4 different sea level rise scenarios that we considered. So that means that these people, their homes would previously flood, but because we provide the shoreline protection, they now do not experience any flooding. And then on the right column here, that represents the people living along other parts of the shoreline throughout the rest of the bay who would experience additional flooding as a result of shifting flood hazards. So these people might not have experienced flooding originally, but when we build this wall, the water is pushed elsewhere, and as a result, they experience flooding. So at low levels of sea level rise, like this first scenario here, the number of people who receive protection is approximately equivalent to the number of people who experience additional flooding, although the demographic composition is quite different. So we see that 61% of the protected population are Black, Indigenous, or people of color, but only 30% of the impacted population are. As we look towards higher sea level rise scenarios, protecting this particular shoreline segment will impact more people externally than it will protect internally, although the graphics are relatively comparable. So as sea level rise continues, this action here is actually harming more people than it's protecting. And so it's really important that we carefully consider these impacts and the way in which they change as sea level rise progresses, particularly for minority populations and marginalized groups. And that will allow for an evaluation of proposed shoreline adaptation projects that can inform more equitable risk reduction. So thinking about not just how many people are impacted, but also who are those specific people who are impacted. So just to kind of summarize what I've just been talking about, we see that in San Francisco Bay, if we take actions in one part of the shoreline, that can have a large effect on both neighboring and also more distant coastlines. However, as I mentioned earlier in my talk, these externalities or these impacts for other communities are rarely considered when we decide whether or not to implement a particular project. Typically, only the impacts to that local coastline in the vicinity of the project are considered. And this could lead to potentially large underestimation of the cost of a project on a regional scale. So I want to give an example of a concrete project that is currently being considered within San Francisco Bay and how we could use this approach to better assess what its actual costs and benefits could be. So this is the case of Highway 37, which is a main transportation corridor that runs along the north part of San Francisco Bay. So we're now up here along the northern shoreline of the bay. And you can see in this map that much of the length of this roadway runs along that OLU 7 shoreline, which is the one that I had just been talking about. So we see that segments of this road are already experiencing flooding during high water events. And as a result of this, the State Transportation Agency, Caltrans, is considering 2 different adaptation alternatives to try to mitigate the effects of future flooding. So the first of those would reconstruct the road on top of a raised levee or an embankment. And that's estimated to cost about $650 million. So this option essentially mirrors the shoreline protection scenario that we implemented in our model. And it basically provides a hard barrier between the bay and the marshlands and other agricultural areas within OLU 7. So it disconnects the bay from those marshlands. And when we did that in our model and ran that scenario, our analysis estimated that this action would lead to a net increase of about $300 million in damages across the rest of the bay for the highest sea level rise scenario that we considered as a result of the loss of flood storage space in this region and induced flooding that occurs elsewhere. On the other hand, on the other hand, we also have the second scenario, which is constructing the road on a causeway or an elevated roadway. So you can see here a causeway would still allow water to move underneath the road and thus would allow the bay to remain connected to these low-lying areas within OLU 7. And this approach is estimated to cost between $2.2 and $2.5 billion. But because it doesn't cut off the connection between the bay and the marshlands, it doesn't cause additional flooding for other communities elsewhere. So while option 2 is clearly more expensive from just the construction side of things, we can see that option 1 will cause non-negligible impacts for other parts of the bay. And as a result, considering the feedbacks and the shifting flood hazards that may accompany our choice of whether to implement a levee or a causeway is really critical to properly evaluating these proposed projects and selecting appropriate mitigation strategies that provide benefits in the location of the project, but also do not cause additional issues for people elsewhere. So in addition to considering impacts to structures and individual infrastructure components, coastal communities are often also concerned about impacts to critical infrastructure systems as a whole, one of those being the transportation network. So as we all know from driving around the DFW area, if we see a disruption or a closure in one part of the network, that can propagate through larger parts of the system and cause much more severe delays. And in coastal communities, flooding is one potential cause of those types of roadway disruptions or closures, and it can thus reduce the capacity of our transportation network. So we want to understand how will sea level rise affect roadway flooding in San Francisco Bay, and what are the resulting impacts on the traffic delays. So to do this, we take our flood outputs from our hydrodynamic model, and we overlay them with the transportation network for the region. And then we run a traffic simulation model that allows us to estimate which links experience the largest delays and how do those propagate through the system over the course of the model simulation. So the model that we're using here is called MatSim. It's an agent-based behavioral model that consists of basically a sample of individual commuters, and each of those commuters can adjust their travel plan in response to flood disruptions. And then the model will rerun and consider what sort of delays result from that. This model was built using GPS cell phone data collected from local commuters, so it is reflective of the general travel patterns in the region. So using the model, we can implement flood disruptions in certain locations and then simulate a typical morning commute to see how the travel patterns will change and how the traffic delays will propagate throughout the rest of the system. And you can see an example of that here on the right. The map is showing the average travel time delay for commuters on a census tract basis due to a 1 meter sea level rise flooding scenario. And so if we simulate 1 meter of sea level rise, cut all of the roadways that experience flooding as a result, then we rerun the model and we determine where do those major delays occur. And you can see here that large areas in the north part of the bay up here, as well as some areas in the south part of the bay, shown in orange and red, could experience delays of upwards of 30 to 60 minutes during the morning commute. So even though these roadway flood disruptions are rather localized along the shoreline, the regional impact can be very large due to the interconnected nature of our shoreline or of our infrastructure systems. And so this, this result that I'm showing here assumes existing shoreline conditions without any new adaptation actions. But we also want to think about how our decisions as coastal managers could additionally impact this particular system. And so for this study, we wanted to quantify how the travel times would change for commuters in one location as a result of shoreline protection being implemented in another location. So again, we chose to focus on San Francisco Bay, in particular the south part of San Francisco Bay, where roadways are often located right along the shoreline and thus are susceptible to flooding. In this figure on the left, you can see the roadway network in the 3 counties in South San Francisco Bay, and the major highways here are highlighted in orange that run sort of north and south along the bay, and then also bridges that cross east and west. And these counties include Alameda County on the eastern shoreline, San Mateo County here on the western shoreline, and Santa Clara County on the southern shoreline. So in this case, we ran 4 different shoreline scenarios. The first was a no protection scenario. So this is just using existing shorelines, no additional protection provided. Then we ran 3 additional scenarios in which one county's shoreline was completely protected from flooding by a seawall, while everyone else's shoreline was allowed to remain in its current condition. So you can see those examples here protecting the Alameda County shoreline on the east, the San Mateo County shoreline to the west, and then the Santa Clara shoreline county to the south. These black lines show those seawalls that were implemented. And then the resulting roadways that become flooded are shown here in red. So you can see where those where the flood disruptions are typically occurring in each of these scenarios. And then we calculated the total travel time for commuters in each of these counties to see how they would be impacted. So the results that we calculate here are highly dependent on the physical structure of the transportation infrastructure and network in each county, and also on the availability of capacity within each roadway. But we can see that shoreline protection in one county can increase travel times by more than 10% in certain scenarios. So these bold values here indicate scenarios that cause an increase in travel time as a result. And this is, it's going to exacerbate traffic issues during the morning commute, which is already quite a challenge for many people living in the region. So even just a 3% or a 7% or a 10% increase in travel times could be substantial. So just to provide one example here, if we protect the eastern shoreline in Alameda County, that causes, so that's shown here in purple, that causes additional flooding in Santa Clara County here in green and leads to additional roadway disruptions. And as a result of that, travel times for commuters in Santa Clara County increased by about 7.2% on average. So again, this demonstrates that when we consider how to adapt our shorelines for future flooding, it's important to remember that those flood externalities that I discussed previously will also lead to disruptions within our infrastructure systems. And because of how interconnected our infrastructure systems are, those disruptions can propagate throughout the network and potentially affect the overall system performance. All right, so to summarize, we see that given these local shoreline actions, whether we decide to implement seawalls in one location or not, that can shift risks to neighboring and more remote stretches of the shoreline. And we see that both through an increase in flood volumes, increases in economic damages to structures, as well as potential degradation of infrastructure performance. We also saw through the initial analysis that the types of landscapes that we decide to protect or to not protect can play a critical role in determining how our shoreline actions change regional water levels and flooding. So remember, when we protect those wide alluvial valleys and cut off the low-lying flood storage areas from the bay, that leads to the most substantial increases in flood volume, damages, and infrastructure impacts throughout the rest of the bay. So really thinking about which pieces of our shoreline are most appropriate for protection and warrant protection versus which ones could potentially be used for strategic flooding, where we allow those areas to absorb water and thus protect other areas and provide benefits for more developed pieces of the shoreline. So looking forward in terms of, what does this mean for coastal communities and their future adaptation planning? I think it's very critical that we consider the feedbacks between human decision making and natural hazard extent and severity when we're creating these adaptation plans. So rather than just looking at, what is the existing hazard, we really want to think about how do our actions at the shoreline affect the extent and severity of our flooding, and then what are the implications for future flood events. In addition, there is, I think, a large opportunity to leverage coordinated approaches to adaptation planning that will help to enhance regional resilience, particularly in areas like San Francisco Bay, which have a lot of interconnections, while at the same time trying to minimize the negative impacts that might occur due to individual communities making their own decisions. So thinking about, is it possible to come up with a plan at the regional scale that can consider these interactions and hopefully provide equitable risk reduction across the entire region, rather than just telling each community to go it alone and try to figure out their own plans, while at the same time potentially causing additional issues for other communities. So based on this work that I've presented today, we've already had a number of really promising discussions with stakeholders in the San Francisco Bay Area about how this analysis and this approach could be applied to on-the-ground planning. So thinking about how could we evaluate current infrastructure plans given the modeling approach that we've developed. And then we've also been talking about how the governance and policymaking structure in the region could potentially evolve to better manage this threat of sea level rise. So thinking about potentially moving towards a more regional perspective. So for me, it's really promising to see how the understanding that was brought about by this research has catalyzed a discussion about looking towards more comprehensive and equitable planning within the San Francisco Bay region. So with that, I want to acknowledge the funding agencies who supported this work, the National Science Foundation and NOAA, as well as my collaborators at all of the institutions shown here who have made this work possible. If you're interested, I've put some of the relevant publications here. You can feel free to take a look at those if you'd like to learn more. And then I'm happy to take any questions. Thank you everyone for attending and for participating today.
Thank you very much, Dr. Hummel, for your presentation. Certainly a very interesting topic and very relevant with the current changes in our climate and the kind of natural disasters that we are facing and increased tidal activities. So very, very pertinent research. So to everybody, if you have questions, please type them in the chat window and I'll read them out. So while people are doing that, I actually myself have a lot of questions for you. So if I can start with one of them, which is, your models that you use. I guess you called one of them your hydrodynamic model, and then you interfaced it with the other kinds of models like infrastructure models and traffic models and so on. So what exactly are these models? Could you demystify them a little bit? Are they mathematical models? Are they predictive models? I mean, when you use the word model, I was just kind of curious to know what.
Sure, yeah, so they're numerical or mathematical models, but basically they allow for example, the hydrodynamic model allows us to calculate water levels and water velocities at different points throughout the model domain. And then we can force the model with different water levels, different sea level rise scenarios, different shoreline conditions, and then rerun that model to see how do water levels at each of these different locations change. And so this particular model is solving basically fluid mechanics equations in a numerical sense. So we can run these on high performance computers to calculate those values at every location within the model.
So, okay, so how do you map it to real world applicability? I mean, you obviously cannot build a levee and see what happens, right? So, I mean, how do you know how good the model is only as good as the kind of inputs you give it, right? So.
Right, so the model is calibrated using historical events, historical tidal data, and historical storm events. And so you can kind of adjust the parameters in the model to make sure that the flood extent is matching what we would see previously and that the water levels are behaving as they would historically. And so there's not an exact comparison that you can make, obviously, as you said, because we can't implement these structures directly.
Can you, excuse me, can you even build a kind of a small lab scale? I don't know. I don't. I mean, it's no longer a simulation, but a small lab scale scenario where you actually have water flowing and little levees built to see how things change, or is it going to be completely based on these numerical simulations?
Yeah, so actually the Army Corps of Engineers back maybe 50 years or so ago built a scaled model of San Francisco Bay, and with the purpose of understanding how different structures would affect flow. And so they do model different conditions of tides and river inflows and look at how that affects velocities and water levels throughout the bay. They haven't applied it for, it's more of an educational tool at this point. It's not actively being used for research, but it would be interesting to apply a similar approach to evaluate these types of shoreline actions as well.
So there's a question from the audience. Can I get the PowerPoint for this session? I would imagine so. We should be able to have that available. If not, on the website, you can certainly send an email to Dr. Hummel and she'll be happy to share it, I assume. So if I can continue with a few more of my own questions. So, when you look at human history, right? I mean, a lot of, so I'm being philosophical here, I guess. A lot of human development has been dictated by climate, people and natural features. People build things near rivers because they can get water. They build in the shadow of a hill because they don't want to get exposed to maybe harsh winds and all that. But that was in the past. Now it seems to be that there are other reasons why development happens, right? I mean, in the South Bay, as you mentioned, development is happening in spite of the natural disasters and the natural challenges that are out there. Why is that? Do you have any? I know this may not be your area of research, but I'm just curious.
Yeah, I mean, I think there's a number of sort of overlapping factors, but I think one of the things is just generally our zoning and planning sort of regulations within these regions is not really appropriate for the disasters that we're facing now. So in a lot of river systems and coastal areas, there aren't as many restrictions on building in flood zones, or the flood mapping is not adequate to really identify all of the areas that are actually vulnerable to flooding. And so some area might be zoned for development, but it might still have some kind of inherent risk. And especially as we look forward to future hazards like sea level rise, which haven't even played out yet, those aren't even incorporated into the flood maps that are used for regulating development yet. So I think one piece is just, if you have these high property values, people are still going to build there regardless of what kind of risk exists. And as long as it's allowed based on the policies within that particular region. So I think there's a need to think about how are we going to kind of rethink our zoning policies and our development policies to account for these future flood risks, and not just look at historical events.
I see. And early in your presentation, you talked about how, like for example, hurricanes are increasing in intensity over time, right? So are your models time sensitive? I mean, are they predicting what might happen if we don't take action, what might happen 10 years from now, or are they sort of for the current scenario?
So the model for San Francisco Bay doesn't use any kind of hurricane forcing in it. So the way that we're looking at the temporal change is just implementing different sea level rise conditions. So we're not necessarily tying them to a time frame, but just modeling possible future scenarios, which could happen at different points in time, depending on what the sea level rise projections actually end up looking like. There are ways that other groups are looking at to sort of understand how do tropical storm climatology, how will it change in the future, and what could those storms look like? We saw Harvey was an unprecedented storm. What other hurricanes might we see hitting the Gulf or the East Coast as a result of climate change? But that's not something that I've been working on so far. It's more focused on sea level rise and projecting possible future conditions under a scenario-based approach.
I see, okay. And your research, it's in the Bay Area, right? How specific is your research or your findings or models to the Bay Area? I mean, can they be easily translated to the Texas coast, where we all live right now? I mean, we don't live at the coast, but we're from Texas, right? So.
Right. Yeah, that's a great question. So the models that we're using are specific to San Francisco Bay, but the framework that we've developed is definitely applicable to other similar coastal systems as well. So, places like Galveston Bay, or if you're looking at Chesapeake Bay on the East Coast, all of these embayments kind of have some amount of interaction from one part of the shoreline to another. And so by developing, specific hydrodynamic models or specific transportation models that are relevant to those areas, you could use the same framework, the same coupling framework to understand how that particular region would be affected, whether that's by sea level rise or hurricane events as well.
So this is a question I ask a lot of presenters. So what would be the surprising conclusion that your research has revealed that you would not have maybe derived through common sense? I mean, we are using sophisticated models and we're coming up with some conclusions. Is that something which would make the common man say, aha, I would have never thought of that?
Yeah, I think the main thing that honestly surprised us looking at the results of these models, and that I think kind of opened the eyes of some folks in the region, is that even if these actions that we take, these shoreline protection actions, are relatively small, they can still lead to quite large feedbacks within the bay, and that can cause damages not just for neighboring shorelines, but also extending regionally. So the magnitude of that impact was not really well understood or identified previously. And so I think, that's something that's really forcing people to say, to kind of step back and take a look at their existing plans for shoreline adaptation and think about whether the approach that we're currently using is really appropriate, or if we need to perhaps approach the problem in a slightly different way, perhaps using a more regional perspective.
Okay, great. Okay, so we are at 1 o'clock, so I want to respect everybody's time, and I would like to, thank Michelle again for giving this great presentation, and looking forward to applications in our neck of the woods, maybe some application in the Galveston area or Texas or Louisiana, where we have a lot of issues of this nature. That'll be exciting. For the rest who are attending, we will be continuing this series, so please keep a lookout for future presentations, and I'll be hosting a few of them. So look forward to seeing you again. Everybody, thanks and have a great rest of the day.
Thank you very much.